So today we'll talk about pre-training for time series. And we plan to cover the following papers. So on the high level, we'll talk about what's supervised versus unsupervised learning and what's contrastive learning. And lastly, we'll also see how to do unsupervised learning or contrastive learning in the scope of time series. So for supervised learning, if we think about time series forecasting, it's when we have the input and we want to predict some label. So the input in our case will be the context, and the label will be several time steps into the future. For unsupervised learning, it's when the labels are not always available. So the most intuitive case will be for classification, where you maybe have some time series windows but you don't know which classes they belong to, or you have a bunch of images, you don't know which categories they belong to. So in that case, you will want to do unsupervised learning, where you don't have access to the labels, but you want to learn the high-level representations of those time series windows or images or anything. And the way you do that is by because you don't have access to labels, so you need to define some additional task for the model to solve at the pre-training stage. So it can be we add in some noise to a time series and want to reconstruct the original time series. Or for images, maybe we can cut the image into patches, and then we ask the model to tell us what's the right order for those patches. So we'll first look at a paper from 2021. So here we have a time series window of W number of time steps and M number of variables. And our pre-training objective is to reconstruct some time steps that we masked. So by masking the time steps, we'll simply put zeros at where the variables or the time steps are masked. And then the objective will be to reconstruct those masked time steps. So we can use objective functions such as MSE. So the way we do this is by still having a feature vector at every time step. And maybe for some variables at that time step, we choose to mask that variable. And then we feed in those feature vectors or those feature vectors at each time step into a transformer model to get the Z1 all the way to ZW as our output embeddings. So maybe you can choose which variables to mask independently. So you don't have to mask all the M variables at once. You can just choose to mask two of the M variables. And then at the next time step, you might choose to mask a different set of variables from those M variables. And another trick that the model observed is that instead of just masking a single time step once, it will make more sense to mask several time steps at once. The reason is that if we just mask a single time step, it will be very easy to infer what's the original value based on the previous time step, as well as from the next time step. So we can maybe just take the average from previous time step and from the next time step to get the imputation for current time step. And we don't want that to happen because we want our model to learn some high-level representation. So to make the task more challenging, we'll mask several time steps at once. And based on those Z1 to ZW, which are our output embeddings from transformer encoder, we'll add an additional linear layer for each of those embedding vectors. And the linear layer will try to reconstruct the original M variables. So ideally, the x1 hat we will want the x1 hat to be as similar to x1 as much as possible. And we'll do that via the MSE loss. And this is what we do during the pre-training time. And then during the downstream time, we can further fine-tune the model for some different downstream tasks, such as classification, regression, or forecasting. So the way we do that is we take all the output embeddings from the transformer encoder. So we take all these Z1 all the way to ZW and then concatenate them. So we get a vector of size D times W, where D is a hidden dimension of a transformer and W is number of time steps. So we take this long vector and then feed into additional linear layer to do either forecasting or do classification. So for forecasting, the output will be the number of prediction steps. So linear D times W, comma prediction length will be the parameters for our linear layer. And for the case of classification, our output will be the number of classes that we have. And in the initial stage, we actually want to keep the transformer encoder to be frozen. We only want to train the linear layer at the end. The reason is that initially the linear layers will be randomly initialized while the transformer encoder is already pre-trained. And with a set of randomly initialized weights for linear layer, their signal will be very, very noisy when we backpropagate the gradients back to the encoder. And this will negatively disturb the weights of the pre-training encoder model. Because we don't want that to happen, so we want to keep the encoder frozen at first. And then once the linear layer is outputting something that's more reasonable, then we can unfreeze the encoder part and then fine-tune both the encoder and linear layer at the same time. And here are some results. Static here means that we keep the encoder part frozen and we only train the linear layers. And fine-tune means that we've gone through both stage 1 and stage 2. So we fine-tune both the linear layer as well as the encoder. And we see that with just a linear layer, the computation time is very fast. And with additional fine-tuning, we're able to improve the performance even more compared to just training the linear layers. And the paper also did some experiments on how to mask those different time steps. So it tried mainly two things. One is how we should mask the M different variables. So separation, SEP stands for separately. So we try to mask M variables separately at a given time step. And then an alternative is to mask those M variables all together at a given time step. And second variation that they did is to compare the Bernoulli, which is we mask one step at a time, or stateful, which means that we mask multiple time steps at a time. And the table shows that all combinations can give us some good performance, but out of the 4 combinations, we actually are able to get the best performance from masking the M variable separately and also masking multiple time steps at once. So masking one time step at once will correspond to the issue that I mentioned earlier, that if you just want to predict time step t, maybe you can just take the average of time step t minus 1 and time step t plus 1. So the model will not likely or less likely to learn those high-level representations. And lastly, the paper also did an additional experiment on showing the performance of the model by doing pre-training versus just by doing supervised learning. So we see that almost across all the tasks, the model can get the best performance by doing this kind of pre-training. And the second method I want to talk about is called contrastive learning. And the high-level idea is that given a bunch of objects, you want the embeddings that are coming from the same object to be more similar versus embeddings coming from different objects. And by similarity, we can just use the dot product. So an example will be the three images on the left, where we have the anchor image in the middle, and we have a positive image as well as negative image. So we want to maximize the distance between the anchor image versus the negative image compared to the anchor image versus the positive image. And because we're dealing with unsupervised learning, we don't really have access to the original labels. So the positive samples can just be generated by applying some form of augmentation. For example, we can crop the image or do some rotation on the image. And negative samples are all the other samples from a data set or from the current batch. And in this inequality, the left-hand side will be the measuring distance from the representation of the anchor image to the positive image. And then on the right, we have the distance from the anchor image to the negative image. And we want the distance to be at least alpha amount smaller compared to the negative image, compared to the image to the negative image. And we can rewrite it into a loss function, which is called the triplet loss. And this is also the high-level idea of the info NCE loss. So you will try to make the dot product as similar as possible with the positive image compared to all the other images in your current batch or your current data set. And one observation that people had when dealing with contrastive learning is that contrastive learning typically requires a large number of negative samples to work well. So the method that we showed on the last slide is the end-to-end method on the left. So where you have an encoder for your query image or your anchor image from previous slide. And you also have an encoder for a key, which is either a positive image or the negative image. And the vanilla implementation is to backpropagate the gradient back into both the encoder for the query as well as the encoder for the key. But the issue is that if you have a large number of negative samples, your memory will explode. So one way to deal with this is to just to have a memory bank that keeps track of the negative embeddings from the previous batches. So once we have a memory bank, maybe we can have the encoder Q and the encoder K to share the weights. So this will correspond to the image in the middle. Because both the encoder Q and the encoder K are sharing the same set of weights, we no longer need to backpropagate the gradient into the encoder for those positive and negative images. However, one issue with this approach is that across the different batches, maybe the encoder will update over time, and the samples can be very inconsistent from batch to batch. And this will cause an issue. So what this Moko paper proposes is approach on the right. They use the momentum encoder, which only updates the encoder for the key a little bit based on the current query model, based on the query encoder. So if you look at the equation at the bottom, they actually use a very large number for M, which is very close to 1. And they actually did an experiment that for the momentum parameter, we always want to use something that's very close to 1. So for something that's very close to 1, that means that we don't actually update the momentum encoder that much. We keep it fixed most of the time and only update it a little bit over time. And same thing as with the memory bank, because we are no longer backpropagating the weights into this momentum encoder, we can save a lot of memory. And this will allow us to use a larger number of negative samples. And now let's look at how this contrastive learning idea works for time series. So this is another paper from 2021 called TSTCC. So given a time series window, we'll do a strong augmentation as well as a weak augmentation. And we'll pass it into 2 different encoders. And the idea is that it actually have designed some unique task that's specific for time series. So instead of just trying to match the embedding for the encoder with a strong augmentation with the encoder with a weak augmentation directly. So instead of just matching this embedding vector C directly, it will actually try to predict this. It will try to match the C with this input vector Z before the transform model, and to try to predict several time steps ahead. So instead of matching with ZT, it will try to match with ZT plus K. So we'll try to predict K time steps ahead. And in addition to this temporal contrasting, I also have this original contrasting from the same time step. And your final loss function will be a combination of those two type of loss functions. And in this paper, one experiment that they did is to change the amount of label data. So you might have a data set, but you might not have all the ground truths for this data set. And more specifically, they're dealing with a classification case, which is given a bunch of time series windows and a predefined number of classes. You try to classify which class the given time series window belongs to. So you might not have the label for your entire data set. You might only have the label for a percentage of the data set. And we see that with this pre-training, we can actually get the most improvement over the baseline model, which is a supervised model, when there's a limited number of label data available. And even with 100% of label data available, we still see there's some improvement by doing this kind of pre-training. And I also did additional transfer learning experiment to show that the representations learned by contrastive learning is actually transferable across data sets. So they have a total of 4 data sets here. And then they, for the supervised approach, they directly train the model on the source data set and then apply it on the target data set. So for example, first column will train the model on the data set A and then apply it to data set B. And compared to this approach, if we use contrastive learning, when we do pre-training and fine-tuning both on the source data set, we can actually learn representations that are more transferable across the data sets. That's because we see that on the second row, it tends to behave better on the target data set. So the takeaway here is that by doing this contrastive learning, we can learn more high-level representations that are transferable across data sets. Now let's actually go back to the first approach that we presented. So the image on the left is the approach that I showed on the first slide. So we mask a random subset of the variables and a random subset of the time steps, and we try to reconstruct them. And you might notice that this approach is very similar to the BERT model. So in the BERT model, given a sentence, it will try to it will mask out some of the tokens in the sentence, and will try to reconstruct those tokens. And this paper masks autoencoders as pre-training. It actually applies this mask reconstruction idea to computer vision. So the reason I want to talk about this paper is because it highlighted a lot of the differences on doing the pre-training in NLP compared to the pre-training task in computer vision. And we can probably leverage the idea and then see how it is also different for time series. So this paper first noted that for images, the information density is different. So for languages, most of the time, we cannot take out a large amount of tokens from a language, from a sentence. But for images, the information density is typically much lower. We only care about the very high-level semantics of image. So instead of using a lower masking ratio, we actually, for images, will use a masking ratio of 75%. So some examples are shown at the bottom. So with 75% of masking, it's um, most parts of the image will be masked, but you can still see um, the you can still tell what's originally in those images a little bit. And they also do the masking by patches, so they don't just mask the original pixels. Another difference that they highlighted is that while BERT uses a very simple decoder, so in the original BERT model, they just use several linear layers. But for images, the reconstruction task is a little bit harder because we want to learn those high-level representations for those images. So instead, we will try to use some more of a more powerful decoder model, such as a transformer model. And this is their overall architecture. So given the input, they'll first cut it into patches, and then they'll mask out 75% of the patches. And the target will be to reconstruct the mask patches. It will first feed into an encoder model, and then based on the output embeddings of the encoder model, it will feed into a slightly smaller decoder model. And the objective of a decoder model is to reconstruct the mask patches. And if you have time, I would advise you to actually read their code because their code is very easy to follow. And during their training, on the x-axis, they show it's the number of training epochs over time. And it shows two different approaches to utilize output representations. So it's one way is to do end-to-end fine-tuning, and the other approach is to just do linear probing. And we see that there's the model actually able to learn representations that are beneficial for both linear probing as well as for fine-tuning. But one issue to note here is that if we're doing linear probing, because in the original pre-training task, we use several layers for decoder. If we just use one layer for the decoder part in the linear probing, we will get a little bit worse performance because the task is very different from the pre-training task. And also compared to the contrastive learning approach. So some of the drawbacks of using the contrastive learning approach is that contrastive learning requires a lot of good augmentations that are tailored for the specific domain or specific data set. And if we apply contrastive learning, it tends to saturate earlier on compared to if we use this mask autoencoder approach. And we also get better performance with this mask autoencoder approach. The paper showed a bunch of experiments, and I will just talk about a few experiments I want to highlight. So first graph is when they change the masking ratio. So we see that it actually works quite well with a wide spectrum of different masking ratios. And they also try to change the number of decoder layers. And even for this mask autoencoder approach, you can still do augmentation by doing cropping and other kind of data augmentations. So the takeaway here is that when you try to when you're trying to define the pre-training task, you want to define the pre-training task to be very similar or as similar as possible to the downstream task. So maybe in the case of time series, maybe you want to always predict the future instead of just predicting some time steps in the middle in the context window. And we can also think about how this pre-training task should be designed differently for time series. And this is a paper that I think we talked about last week, which is we instead of treating every time step as a separate token, we group multiple time steps into a patch and treat each patch as a token. So the idea will be the same. So we just mask out several patches from the original time series and try to reconstruct them. And in this paper, they choose 40% to be the amount of patches that they try to reconstruct. And for a downstream task, the their approach is very similar to the previous approach that I talked about. So they take all those output embeddings from each of 10 steps and they concatenate them together and then feed into a linear layer at the end to solve the target task. And in the first experiments that they showed, they show that by doing this kind of pre-training, they get better performance compared to the supervised approach, where we just train the model to predict into the future. And here, their pre-training task is still to mask a random subset of the context window. And they also show that their representations that they learned by doing this pre-training can actually be transferred into different data sets. So they pre-train on the electricity data set and they transfer it to weather and traffic data set. For the supervised approach, they do both the pre-training and fine-tuning. So, sorry, for a supervised approach, they just train on the downstream data set from scratch. So some takeaways here is that whether MAE will be the best objective to do pre-training and whether we want to, because this paper masks out some time steps in the context range and then try to reconstruct it. But for forecasting, we only care about predicting you into the future. And the type of information that we care about for doing reconstruction in the context range versus predicting to the future are very different. So which objective should we define for the pre-training task? And lastly, I want to also talk about a paper on studying the representations that are learned from doing this kind of pre-training or from across different models. So it uses by default, it's the original model. And by this green bar, it shows instead of having this pre-trained or trained supervised transformer encoder, it randomly initializes the transformer encoder and keep it frozen. So it doesn't really train the transformer encoder. It actually shows that for all those transformer-based models, there's not really a drawback of using a randomly initialized feature extractor versus a trained feature extractor. And most of the information are actually learned by just the linear layer at the very end. So most of the transformer encoders are not really helpful when solving the task. So actually running out of time here, but some takeaways are what are some good data augmentation strategies and how's the pre-training task different for time series compared to NLP or computer vision? And lastly, for those pre-trained models, how can we probe or visualize what kind of characteristics actually learned by those models?